Okay, this is going to be the last video on the videos involving center of mass. And if you haven't done it yet, I would watch all the previous videos. There's 7 of them altogether. And most of those videos involved working with vertical rectangles with everything in terms of x. Now, in the last video, which was example number 7, we actually derived these formulas for horizontal rectangles with everything in terms of y. So you might want to watch the example 7 video before we do this one, and we'll run through these series of steps. Now, this is to find the center of mass, and this is what we've used in previous videos. So first of all, step number 1, we found the total mass of the system. You found the moment about the y-axis. You found the moment about the x-axis. Then you use those things to find the x and y coordinates of the center of mass. And if you watched the previous videos, hopefully you're pretty familiar with these by now. Now, if it's just these 5 steps, this assumes that you know the intersection point between the 2 curves that you have. If you're not given that, then there's actually going to be one extra step, and we'll go ahead and put that in here now. We'll call it step 0. And the first step would be to find the intersection of the 2 curves. Then you can find the mass between them. And on the problem we're going to work this time, we'll actually have to do this. So we'll actually have a step 0, initial step to find the intersection points. So with this, let's take a look now at a specific problem. And in our specific problem, we will have this. So suppose you're given 2 curves. And the first curve is, you've got x is equal to 9 minus y squared. Second one, x plus y is equal to 3. Now, one of the first things that you always run across in here is how do you know whether you have to use vertical or horizontal rectangles? See, do you want to put everything in terms of x or everything in terms of y? And it helps sometimes to have a graph first. So let's go ahead and suppose you sketched out a graph of these things. And what it would look like would be this. Now, what we're going to do on this first one is let's take a look at what would happen if you elected to use vertical rectangles. And in this case, this would actually be a mistake, but let's take a look at why it would be a mistake. So I'm going to go ahead and put one vertical rectangle in here. Now, if you put a vertical rectangle in, then that means the thickness of this rectangle is dx. So everything is going to be in terms of x. Then, if you found the intersection points, so suppose we found it, we want to go from here to here. If it's all in terms of x, that means that you're going to integrate from here to here. And that's going to be the integral. So, to show why this thing doesn't work. Now, if you did this, let's go ahead and put some additional vertical rectangles in here. So I'm going to go like this. If we just continue to put vertical rectangles in here, and watch what happens when you get to the final endpoint of the interval. It actually stops right here. So what would happen is you would find this area, but the trouble with vertical rectangles is that it stops right here, and it doesn't account for any of this area over here. So in this case, you get some kind of an answer, but it wouldn't be right because vertical rectangles did not account for the entire area between the 2 curves. So in this case, vertical rectangles would be a poor choice, and you want to pick whichever one does account for the whole area. So now let's take a look and see what horizontal rectangles would do. So we'll get rid of the vertical ones, and suppose this time, let's go ahead and put a single red rectangle in here. And this one's going to be horizontal. Now, in this case, the thickness of the rectangle, this one is going to be dy. So this time, everything will be in terms of y. Now, when you do this, you're going to have, and we'll go ahead and put it right here. Here's an intersection point here. Here's an intersection point here. And this time, if you did everything in terms of y, you'd go from here down to here, and you'll integrate it through this range right here. Now, let's do the same thing. Let's sketch the remaining rectangles and see what it looks like. So if I were to just sketch horizontal rectangles, and I went all the way across here, they would look like this. But notice that this time, within the limits of integration, the horizontal rectangles do cover the whole area. So in this case, picking horizontal rectangles would be the correct choice. So the rule of thumb is, which one do you use? And the answer is, use the one that captures the entire area when you do the integration. So in this case, we're going to work this entire thing based on horizontal rectangles. Okay, so with that out of the way, now we'll go ahead and run through the problem here. Now again, given these 2 curves, let's go ahead and do this. So what I'm going to do is, first of all, I've decided, I know I'm going to use horizontal rectangles. So the idea is to put this thing entirely in terms of a function in terms of y. So this one is already x in terms of y. So on this one, I'll take this and make it be this. I'll let x be equal to 3 minus y. Now, as we talked about in the previous videos, if you're going to use horizontal rectangles, it's really, if it was vertical rectangles, it's whatever the curve is on the top minus what the curve is on the bottom. If you're going to do this, it's the curve on the right minus the curve on the left. So if we looked at our thing down here, this would actually be f of x is going to be whatever curve is on the right, f of y is, and then minus whichever curve is on the left. So this blue curve is on the right, the red curve is on the left as you look across like this. So what that means is that this one is going to be f of y, and that would be equal to 9 minus y squared. And this is the one we're going to call g of y, and that's going to be equal to 3 minus y. So let's go ahead and put those two on there. So if we did, you'd have this. So the blue curve is going to be f of y, and the red curve will be g of y. So the blue curve's on the right, red curve's on the left, and it looks like this. Okay, now let's go ahead and run through the steps on this thing. First thing we'd like to do, now in this case, if you've got the graph, you can get the intersection points on the graph, but let's pretend that we didn't have this graph and we were actually going to solve for the intersection points. If you wanted the intersection points, all you do is set f of y equal to g of y and solve for y. So in our case, we would have 9 minus y squared is equal to 3 minus y. Now I'm going to take everything and move it to this side. So I'll have 0 is equal to, this will become a positive y squared here, minus y, and then this will become a minus 6. So if you factor this, this will factor into y minus 3 and a y plus 2. So you've got it factored. Now set each factor equal to 0. Set that one equal to 0 and that one equal to 0. If you solve this one, you would get y is equal to 3, and there's one intersection point. If you solve this one, you'd get y is equal to a negative 2, and there's another intersection point. So what those are, here is the negative 2, and here is the positive 3. So those are going to be your two intersection points. So you're actually going to integrate it from here down to here, and the integral will run across these limits. So we'll put it down like this. So we're going to integrate it from here to here. So now you've got the limits of integration. So in your problem, what that means is you're going to integrate it from negative 2 to 3. So this would be A would be negative 2, and B would be 3. So step 1's done, you've got the intersection points. So the next step, you want to find the total mass of the system. Now let's assume, in this case, rho is the density. So in our problem, let's just assume that the density is equal to 1 kilogram per square meter. We'll assume all this thing is in terms of square meter. So we're going to have 1 kilogram per square meter is going to be the density. Okay, now it's just a matter of running through the integrals and using the correct formulas. So let's start with this. First of all, to find the total mass of this lamina. So the mass is going to be equal to, and just follow the formulas at this point. Okay, the density in our case is 1. We're going to integrate it from negative 2 to 3. So y equals negative 2 to y equals 3. And it's going to be the function on the right minus the function on the left. So f of y is 9 minus y squared, and g of y is 3 minus y. So that's going to be 3 minus y. The whole thing would be dy. Okay, now we will simplify these a little bit if we can. We can make this be 1 times the integral, or else you can just leave that 1 off, negative 2 to 3. And first of all, you've got a negative y squared. Then the negative of a negative, that'll turn into a positive y. And then finally, 9 minus 3, this is going to be plus 6, the whole thing dy. So we'll scoot this down a little bit to right here, and we'll continue. So that's going to be 1 times, now you'll find the antiderivative of this, so this would be negative y cubed divided by 3, and you've got plus y squared divided by 2 plus 6y, and it would be evaluated from negative 2 to 3. Now, at this point, I'm going to let you plug in the 3, then plug in the negative 2, do the subtraction, run through. When you run through all this, you'll actually get this. It'll turn out to be 20.83, and this is going to be kilograms. So 20.83 kilograms is the mass of this flat plate right here. So the whole thing weighs 20.83. Okay, the next thing we need to define is the moment about the y-axis. Now, to find the moment about the y-axis, let's put a couple things on here first just to remind you of where all this comes from. We'll go up to here. Now, if you find the center of mass of just that one rectangle, what the moment about the y-axis is, it's the center of mass times the distance to the y-axis. So it'll be this distance between here and here. So it goes from here to here, and that's going to be the distance to the y-axis. But now the question is, what is this distance? So what's the distance from here? And we'll bring it over to here and say to right there. So what is that distance? And again, like we showed in the previous video, it's just the average between f of y and g of y. So to find that, that would be f of y plus g of y divided by 2. And that's going to be the distance to the y-axis. And actually, I drew it a little too far. It should have stopped right here. So we'll erase that part and stop it right there. So the distance to the y-axis. And again, this we did in the previous video. So if you need to, you can watch and see what that one is. Okay, the next thing you need is the distance to the x-axis. And the distance to the x-axis is going to be this distance right here. So what is that distance? And this is actually the easy one. It's just going to be the y height, whatever that is. So here was the center, and that's the distance to the y-axis, that's the distance to the x-axis, and that's where these come from the formula. So this is the distance, this is the mass, so moment is mass times distance, and again, if you need to, watch the previous videos and it'll show you where those things came from. Okay, so now it's just a matter of plugging things into this one. So let's go ahead and we'll do that. So we want to find the moment about the y-axis. The density is 1. You're still integrating from negative 2 to 3. Then we'll put the brackets here. And again, it's just f of y plus g of y. So that's going to be, we'll put it right here in little brackets. We'll use parentheses here. So f of y is 9 minus y squared. Then you've got plus g of y is 3 minus y in parentheses. Then we'll put brackets across, or parentheses across there, divided by 2. It's just the average value of those two functions. Then f of y minus g of y is the actual height of the function itself. So f of y is 9 minus y squared minus, and g of y is 3 minus y dy. So you've got the whole thing set up. Now it's just a matter of running through that integral. Now, first thing I would do is this, just to make the integral easier, I'd go ahead and take this 2 and bring it to the outside of the integral. So we'll call this moment about the y-axis is, rather than 1, you'll have 1/2 out here in front. And that's going to give you the integral from minus 2 to 3. And now you can go ahead and put these together. So when you put this together, first of all, you've got a minus y squared. Then you've got minus y. And finally, 9 plus 3, this is going to be a plus 12. And that's just putting these two together here. Then on this one, you've got, again, a minus y squared. And you've got this time it would become a positive y. And then finally, 9 minus 3, this is going to become 6 dy. Okay, next step. so that you've still got the 1/2, and that's going to be the integral from -2 to 3. Now, at this point, you've got a trinomial times a trinomial. So to multiply this, just take the first one times all 3, the second one times all 3, and the third one times all 3. So we'll wind up with 9 terms by the time we get finished. So first of all, first one times this. So minus y squared times minus y squared would give you a positive y to the 4th. Then this one times this one will give you a negative y cubed. Then this one times this one would give you minus 6y squared. So that was this first one times all 3. Now you're going to multiply this second one times all 3. So this is going to give you, this times this would be the 2 negatives make a positive, so that's going to become a positive y cubed. Then this times this would become a negative y squared. And finally, this one times this one would become a minus 6y. So that takes care of the second one. And finally, now multiply this third one times all 3. So this times this would be minus 12y squared. This times this would be plus 12y. And finally, this times this would be plus 72. And this entire thing integrated with respect to y. So let's go down a little further. So the moment about the y-axis would be equal to 1/2. And let's go ahead and combine all the like terms. So if you combine the like terms, you've got a y to the 4th. Now, here's a negative y cubed and a positive y cubed. These two will cancel out. Then just looking at the squared terms, you've got minus 12, minus 1, minus 6, which would be minus 19. So that's going to be a minus 19y squared. That'll take care of the squared terms. Then you've got just the y term. So 12y minus 6y would give you a positive 6y. And then finally, you've got this plus 72 out here. So plus 72. So that whole thing, dy. Okay. Next step would be to go ahead and find the antiderivative. So I've got 1/2. And when I do the antiderivative, this will turn out to be y to the 5th divided by 5 minus 19. And I'd have y cubed divided by 3 plus, this would be 6. This would be y squared divided by 2. And I could cancel those out and get a 3y squared. And then finally, this would be plus 72y. Then the whole thing evaluated from minus 2 to 3. Okay, now I'm going to do the same thing I did last time. I'll let you plug in the 3 and then subtract, plugging in the negative 2. And then remember, multiply the whole thing by 1/2 when you get finished. And when you do that, you'll come up with this. This would be 1/2. And that integral will turn out to be 208.35. And then if you take half of that, you would come up with 104. It'll turn out 0.18. And the units on this would be kilogram meters. So that one took quite a bit of work, and that's going to be the moment about the y-axis. So now you've got the moment about the y-axis. Okay, that's the hard one. Now, the next one is actually a little bit easier because rather than having an average here, you just have a simple y. So it makes the integral a little bit easier. But we'll still run through this. So this is going to give you the moment about the x-axis. Again, if you look back up at your picture, this time it's going to be this center of mass times this distance, and that's going to give you the moment about the x-axis. So that's why it's just y. So we'll scoot down and run through that one. Okay, so the moment about the x-axis, the density is still 1 kilogram per square meter, and you're still going to go from minus 2 to 3. This time you've just got y, and still you've got f of y, which is 9 minus y squared, minus g of y, which is 3 minus y. The whole thing dy. Now this one we've already done before, but we'll go ahead and put it right here. That's going to be just 1 times the integral of minus 3. And first of all, we've got y, and we'll go ahead and just put these together. So I've got a minus y squared. Then this is going to become a plus y. And again, 9 minus 3, that's going to become 6. Whole thing dy. Now, take this y and distribute it. So that's going to be 1 times the integral from minus 2 to 3. This will be minus y cubed plus y squared plus 6y, and this whole thing dy. So now find the antiderivative of that. So I've got 1, and this is going to become minus y to the 4th divided by 4 plus y cubed divided by 3, then finally plus 6y squared divided by 2, and if you wanted to, you could cancel out and make it be a 3 there. And this is all evaluated from minus 2 to 3. Now we'll do exactly the same thing we did before. I'll let you plug in the 3, let you plug in the negative 2, and evaluate that. And when you do, it'll turn out to be 10.42 kilogram meters. And what that's going to be is the moment about the x-axis. Okay, so now you've got the total mass, you've got the moment about each axis. So the next step is actually just using these values now to find the x-coordinate of the center of mass and the y-coordinate of the center of mass. So on this one, it's just a matter of looking up the moment about the y-axis, and we'll go back up to here. It was 104.18. So this was 104.18, and the units were kilogram meters divided by, and the mass was 20.83 kilograms. So we'll put that in here. So we've got 20.83 kilograms. Now again, the kilograms cancel out, and if you divide this, you would come up with, and it actually just turns out to be an even 5 meters. And what that's going to be is the x-coordinate of the center of mass. Okay, now in this last one, we'll scoot down just a little bit. You use the moment about the x-axis, which was 10.42. So you've got 10.42 kilogram meters divided by the mass, which is still 20.83 kilograms. And again, kilograms cancel out. And if you divide those, it'll actually turn out to just be 0.5 meters. And that's going to be the location of the y-coordinate of the center. So the center of this thing, the center of mass is going to be, the x-coordinate is going to be 5, the y-coordinate is going to be 0.5, and you will have the coordinates of the center of mass. Now let's go back up and put that on our drawing and see what it looks like. So if you go way back up here to the top, and I think we'll put it in green here, we went over 5, so 5 is right here, and we go up 0.5, well there's 0, there's 1, so it'd be about right here. So if I put a little thing right here about 0.5, that thing right there is the center of mass of that lamina. So really it's just a matter of running through the steps and finding the intersection point first. But the first decision you have to make is whether to use vertical or horizontal rectangles. And just remember, pick the one that allows you to cover the entire area. So in this case, horizontal rectangles cover the entire area when you run through the integrals. So horizontal rectangles would be the correct choice. And as far as the steps goes, we'll take one last look here. It's still just these same steps that we've used in the previous videos. So again, if you need to, look at the previous videos and it'll catch up on all this. So that should be the last video on center of mass, and you've had a couple of examples using vertical rectangles, and this example now using horizontal rectangles.